So simple harmonic motion, this is where we're going to start our investigation into waves. Here's what IB expects you to know about simple harmonic motion. Be able to describe examples of oscillations. And then this whole section here, 4.1.2, is really just a big vocab section. Be able to understand or define displacement, amplitude, frequency, period, and phase difference. Define simple harmonic motion. Whenever you see SHM, that just stands for simple harmonic motion, because writing simple harmonic motion over and over and over gets old. And state the defining equation as A equals negative omega squared times X. We'll talk about that and what omega is, what that means. Solve problems both graphically and by calculation for acceleration, velocity, and displacement during simple harmonic motion. And describe the interchange between kinetic energy and potential energy during simple harmonic motion. So that's kind of our goals for today, to touch on a lot of this stuff, and then we'll wrap it up on Friday. So, vibrations and waves. Okay? Many things in the world just vibrate naturally, and vibrating objects are the source of most waves. Okay? If you think about wave motion and a variety of things, they tend to come from vibrating objects. So, for example, my voice, you're hearing me talk. The sound that you hear is a wave. It's traveling from my mouth to your ears. The source of that sound is my vocal cords vibrating. Okay? So a vibrating object creating waves. When you play a musical instrument, pretty much any acoustic musical instrument, the source is some sort of a vibrating object. You hit a drum, bam, you bang on the drum, it vibrates, it makes sound. You play some sort of saxophone or something, either your lips are vibrating or there's a reed in there that's vibrating, creating sound waves. You play the piano, boing, you bang on the key, it hits a little string, the string vibrates, makes a sound wave. So the source of most waves is some sort of vibrating system, and that's what we're going to look at today, is mostly how we analyze vibrating systems, and specifically simple harmonic motion. So if you have a motion that repeats itself over and over and over and over again, we say that motion is periodic. Okay, we say that motion is periodic. For example, a mass on a spring, and I just happen to have one right here. Here's a mass hanging vertically from a spring. When I don't do anything, it just hangs there. It's in equilibrium. The spring's pulling up, gravity's pulling down, no problem. But if I extend it just a little bit, if I stretch the spring just a little bit and release it, notice that the spring oscillates up and down, up and down, up and down. This is periodic motion. The pendulum motion that you guys investigated in your IA is very much the same thing. When I move the pendulum bob away from equilibrium, it'll vibrate back and forth, oscillate back and forth, back and forth. That motion is what we call periodic. We will also describe simple harmonic motion thinking about a mass on a horizontal surface with a spring attached. If that horizontal surface is frictionless, then we can look at what the mass would do if I stretch the spring just a little bit and then release it. It would also oscillate back and forth, back and forth, back and forth. Okay? So that's what it means to be periodic. What's that? Okay. So let's again, some more vocabulary. The equilibrium position. When you have an oscillating object, it's usually oscillating around an equilibrium position, and that is the point where the net force is equal to 0. Okay? For a pendulum, that would be the vertical position. When the pendulum bob is right in this lowest point, that's equilibrium, and if I just stop it there, it's going to stay there. But if I move it away from equilibrium, it's going to oscillate from one side to the other side and so on. Same thing with the spring. If I can find where this mass would rest, that's the equilibrium position. Now the force of gravity downward is equal to the spring force upward. It's in equilibrium. If I move it away from equilibrium, it's going to not vibrate, but oscillate up and down around that equilibrium position. Okay? A lot of what we analyze with simple harmonic motion will be in relation to equilibrium. What we call displacement is the same thing we talked about displacement in the first quarter of this class. Anytime my object is away from the equilibrium position, the distance it is away from that equilibrium is called the displacement, and that's represented by the letter X. The amplitude of a vibrating object or an oscillating object is defined as the maximum displacement. The farthest distance it gets away from equilibrium, we're going to call that distance amplitude, and it's going to be represented by an X sub 0 on your in your IB equations dealing with simple harmonic motion. Okay? As the object vibrates, one complete cycle is the complete motion it takes to go all the way out and all the way back to where it originated. That we call that one cycle of motion. And so if you think about it, if we start from equilibrium, it goes out, the mass will go out to maximum displacement or to amplitude, back to equilibrium. That's not a complete cycle yet. It has to go all the way out to the other displacement and back to equilibrium again, okay? That would be a complete cycle. Let's see, the period. You guys know this from your pendulum experiment. The period is the time that it takes to complete one cycle. Okay, so period is actually a measurement of time. And it is the time it takes to complete one cycle, which is closely related to this concept that we call frequency. Frequency is the number of complete cycles that an oscillating system does every second. The unit for frequency is the hertz, which is 1 cycle per second. Frequency of 1 hertz is 1 cycle per second. 30 hertz means it oscillates 30 times a second, and so on and so on and so on. And the relationship between frequency and period is inverse. Frequency is 1 over period. Period is 1 over frequency. That's going to come up quite a bit when we study waves. In electronics, actually in a lot of things, we deal with hertz quite a bit. If you guys pay attention to your phones or your computers, you have a processor in there that processes information at a certain frequency. The higher the frequency, the better the processor. You get a Intel 2 gigahertz processor. That's awesome. It's processing at 2 gigahertz, 2 billion processes per second. Okay, that's pretty fast. So let's kind of look at a visual representation of what we're talking about here. So here's my object. It's a mass on a spring on a horizontal surface. Imagine this is frictionless, okay? So no energy is going to be lost to friction. If I pull my mass out, I extend it out a certain distance, that maximum distance that I stretch is called the amplitude. And again, in IB, they don't represent amplitude with the letter A. They represent it with x sub 0. Okay, that's the maximum displacement away from equilibrium. Notice that the spring is trying to pull it back towards equilibrium, okay? When I release it, it's going to accelerate towards equilibrium. When it gets back to this middle point, where the net force is 0, equilibrium position, will it stop? No. Why not? Because it has velocity. It has inertia. It has momentum. All of those reasons. What's that? Well, at that instant, yes. At that instant. But otherwise, it's been accelerating towards that point. Great. So it will continue on because of its inertia, right? Beyond equilibrium over to the other side. And then the spring will start to compress. And as that spring compresses, it starts to exert a force back towards equilibrium, which slows it down and brings it to a rest. And it brings it to rest at exactly the same distance on the other side of equilibrium as where I released it from, assuming this is simple harmonic motion, okay? And then it stops for just an instant and then starts to accelerate back towards equilibrium. And again, at equilibrium, there's no force at all at that one instant, so there's no acceleration at that one instant. And then the whole thing continues over and over and over. And this is simple harmonic motion. Does it kind of make sense intuitively what's going on? Yes? In most of our analysis of motion last semester, you guys, we were dealing with constant force or constant acceleration, right? Remember that? All our equations, distance equals 1/2 at squared, v squared equals u squared plus 2ad, all that stuff. Remember those? That was constant acceleration. Simple harmonic motion is not constant acceleration. It's slightly different. The force changes depending on the displacement. Okay, so it's actually constantly changing. And so it gets really tricky if you start to analyze this in terms of force. So instead, a lot of times what we'll do is we'll talk about energy, because that makes it a little bit easier, because energy is conserved and it's always being transformed from one form of energy to another. But before we get into that, I want to look at this situation and look at graphically at what's going on in terms of displacement, in terms of velocity, and in terms of acceleration. Okay? So let's do that. Here's time. Here's displacement. Think about that mass for a second. Okay? This displacement of 0 is our equilibrium position. Okay? We're going to start by stretching the spring and bringing the mass up to its greatest displacement, what we call the amplitude, right? As I release it, and I watch over time, what's a graph of the displacement versus time going to look like? Okay, and very close. In this case, since we're starting at the top, we're going to call it a cosine graph. But it's going to go like a cosine curve. You with me so far? Okay. How much time has passed when I get to here? Don't give me a numerical value. What's the name of that time period? That's the period. This is one period. Great. And how about right here? Half a period. Beautiful. And here, hopefully you're recognizing that's 3/4 of a period, and so on and so on. Okay? We good so far? All right. So we have a cosine curve. Beautiful. This is our displacement versus time graph. And something to think about, if I took this mass over here that's hanging vertically on a spring, and I attached a pin to it horizontally, and then I started it oscillating, and I took a piece of paper, and I went doot, 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 and I walked sideways while the pin was drawing on the piece of paper, that's what I'd get, right? I mean, it's the same thing. It's exactly what's going on. Doot, 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 and it would do that, okay? So this is the beginning of wave nature, even though that's not a wave, even though the mass going on a spring is not a wave. If I start thinking about how it's moving through time, I get wave functions, okay? Okay, now, let's look at velocity versus time. Okay, velocity versus time. Now, think way back. You guys remember way back first quarter we did dt, vt, and at graphs? Remember that? Okay, great. Just think about that for a second, because there's a relationship here that I'm going to talk about. But before I even get there, let's just think about the situation we have. When I pull my spring out to maximum displacement, what's its velocity? 0. So at this time, velocity is 0. When my spring gets back to equilibrium, at this point, it's going to be maximum. Excellent. In the positive or negative direction. If I displaced it, it's moving from the positive displacement. It's going to have a maximum negative velocity. Beautiful. Okay? And then when it gets to maximum negative displacement, what's my velocity? 0 again. And then here, maximum velocity. Okay? So what am I getting? A sine curve. And technically it's a negative sine curve, right? But it is a sine curve. Beautiful. And then here I'm back to 0. And then here, bless you, here I'm back to maximum and 0 and maximum and 0. Yeah? Everybody see that okay? Okay. So that's just intuitively thinking about it. Let's look at graphically how we actually got that. How do you go from a dt graph to a vt graph? What about a dt graph tells you the velocity of the object? The slope. The slope tells you. And look, what's the slope right here? 0. And what's the slope here? It's negative, and it's the steepest it gets negative. That's our maximum negative. And then back here, I have a slope of 0, and then I have a maximum positive slope. So that's where I get this relationship. All right? If you study calculus, first of all, how many of you have studied sine waves and cosine waves and all that stuff? You've been doing that math? Excellent. If you pursue calculus as well, which I think you guys probably haven't done yet, but when you do, there's two main branches of calculus. There's differential calculus and there's integral calculus. And differential calculus, you take the derivative. You work on what's called the derivative. And by what you do is, by taking the derivative of a function in calculus, you're finding the slope. So essentially what we've done here is if I take the derivative of a position versus time graph, it tells me the velocity versus time. So we're doing calculus kind of without actually doing the calculus of it, just so you know, okay? You guys were telling me that this looks a lot like a cosine function, and that is in fact true. In calculus, if you take the derivative of a cosine function, you will get a negative sine function, okay? So that's just kind of how it works. Now, without doing calculus, let's extend this one more into an acceleration versus time graph, okay? Acceleration versus time. So let's think about what's going on. When the displacement is maximum, what's the acceleration? When the displacement is maximum, I hear 0. So when is the force the greatest on the object? When it's pulled. So when the displacement is maximum, is that when the force is the greatest? Yeah. Therefore, what's true about the acceleration? It's also the greatest. The strongest force is the strongest acceleration is when the object is most displaced from equilibrium, okay? Yeah, F equals ma still works, but now it's just constantly changing, but the equation still holds true. And it's what did you say? And it's also negative because the force is always directed back towards equilibrium. So if I displace something in the positive direction, its acceleration is negative. Great. And then when it's at equilibrium, okay, it's got zero acceleration. That's our definition of equilibrium, right? Net force is zero. And then here it's going to be at a maximum in the positive direction, and so on, and so on, and so on. So we end up with, right? Am I on track here? So we have zero there, and then we have maximum here, and back to zero, and so on. So this is a negative cosine curve, okay? If you were asked to draw these graphs, could you do it? Okay, think about it, because this is the kind of analysis of simple harmonic motion that would be expected of you, all right? So when we talk about simple harmonic motion, again, it's easy to analyze this stuff when you're thinking about a mass on a spring, and whenever you talk about masses and springs, you should be thinking about Hooke's law. Hooke's law deals with springs or elastic objects, and it basically says that the force that is exerted by a spring or an elastic object is equal to negative k being a constant, what we call the spring constant, and that's just telling you how stiff or how loose the spring is, times the displacement. So as I stretch a spring more, I have more displacement. What happens to the force that spring exerts? It increases. So notice that this is not a constant force. This is a situation where the force that is exerted by the spring is directly proportional to how far I stretch it or compress it, okay? Sam? Now, there's a lot of equations, you guys, where it has a negative sign, and I tell you not to worry about it, right? Don't worry about the negative sign. In this case, the negative sign is important. And the reason it's important is because it tells you that the force is directed back towards equilibrium. It's in the opposite direction of the displacement. So if I stretch a spring, it tries to pull it back, and if I compress a string, it tries to push it back. So that's the significance of that negative sign. And the critical thing about Hooke's law is that this is a situation where force is not constant, okay? Force is not constant. If I was to do a force versus displacement graph for a spring or some object that obeys Hooke's law, it would look something like this, right? Notice the force is not linear horizontally. It is linear, but it's not constant. The more I stretch it, the more force is trying to pull it back, or vice versa. And that's supposed to go through the origin. All right? So here's a basic definition of simple harmonic motion. Okay? Any vibrating system for which the restoring force is directly proportional to the displacement, sounds like Hooke's law, and is in the opposite direction of the displacement. So anytime you have a system where if I move it away from equilibrium, there will be a force that tries to bring it back to equilibrium, and the magnitude of that force is proportional to how far I've moved it, you will get simple harmonic motion. All right? So my mass on a spring, classic example. If I stretch it away from equilibrium, that spring tries to pull it back. And the more I move it away, the more it tries to pull it back. And so I will get simple harmonic motion. And the pendulum is the same way. The equation that defines simple harmonic motion, IB throws this in the syllabus, when you have an acceleration that is equal to this Greek letter omega squared x, okay? This is the defining equation for simple harmonic motion. Don't worry too much about it other than this. Know that this is a constant. This is critical. Okay? The acceleration of an object is opposite of its displacement and directly proportional to its displacement. That will create simple harmonic motion. So this is often talked about as being the defining equation for simple harmonic motion. If you have a situation where that is true, you will get simple harmonic motion. Again, since the force is not constant, it's hard to analyze these things using our typical kinematics equations of motion. So instead, it's going to be much easier to talk about the energy when we have simple harmonic motion. That's a little bit easier to analyze. So when you stretch a spring, you exert a force through a distance, right? Yeah? Thinking way back now, what do you get when you exert a force through a distance? What have you done? What's that? Work. And when you do work on an object, what do you give that object? Energy. Excellent. So force through distance does work, gives it energy. So think about my mass on a spring. Just by stretching it, I have done work. And the work I have done has given that spring energy, which in this case is potential energy. And for a spring, the equation for potential energy is 1/2 kx squared. K is not a number that is universal. It's a number that's specific to that particular spring.
Okay, so like if we're doing a
It will be given, or you might solve for it, or something like that. It's kind of like mu. Remember mu with friction? How it varies from surface to surface? K is the same thing, same idea.
find the coefficient for
Or the spring constant. What's the spring constant in this situation? Exactly. Okay. Now I want to just show you real quick where this equation came from. I hate just throwing equations at you without thinking about where they came from. So let's go back to our force versus displacement graph for a spring. Originally I drew it negatively, which I'm going to ignore that negative for a second, just for simplicity's sake here, and go like this. Okay. So the more I stretch a spring, the more restorative force I get, right? Now, when I have a force versus displacement graph, and I calculate the area underneath that graph, what does that tell me? Force times displacement. What is force times displacement? Work. Thank you very much. So this tells me the work. Now, if in a situation, think about this for a second. In a situation where the force is constant, this is super easy. This is just force times distance, right? Okay, but now we have a situation where the force is not constant, but it's still a pretty easy geometric shape to calculate the area underneath, right? How do we calculate the area of a triangle? 1/2 base times height. So I get 1/2 force times displacement. And for a spring, remember from Hooke's law that force is equal to negative kx, right? So 1/2 negative kx times x, or 1/2 kx squared, is the work done, which is the same thing as the potential energy. Okay, so that's where that equation came from. Okay. So this equation allows us to calculate the potential energy when I stretch the spring out maximum. So now when I release it, it's going to accelerate. And what's that potential energy going to become? Kinetic energy. Excellent. So if I want to know the total energy of a vibrating object or an oscillating object, it's equal to the kinetic energy, 1/2 mv squared, plus the potential energy, 1/2 kx squared. That's the total energy that the object has that is oscillating in simple harmonic motion. Now, we have two situations where this simplifies itself a little bit. When the displacement is maximum, when I'm at the amplitude, what's the velocity of the object? When it's all the way out, what's the velocity? 0. So it has no kinetic energy. At that point, the total energy is just the potential energy. When I'm at equilibrium, then there's none of this, and it's all that, okay? And it's always going back and forth, back and forth. If I'm somewhere in between equilibrium and maximum, it's the combination of the two. But at either extreme, it's just one or the other. And the total is constant. Okay? So that's what I'm saying here. If displacement is at the maximum, at the amplitude, then velocity is 0. So at that point, the energy is just kx squared, or ka squared in this case, which is just amplitude. Okay? The significance of this little thing, if you look at that equation carefully, you'll notice that the energy in a vibrating system is proportional to the amplitude squared. Okay? I'm going to say that again. The energy of a vibrating system is proportional to the amplitude squared. Think about this the next time you're playing on the beach. You're sitting there playing in 2-foot waves. This is fun. And a 4-foot wave comes in. How much more energy does that wave carry? 4 times as much, okay? 4 times as much energy if it's twice as big. What if it was 3 times larger? How much more energy would it carry? 9 times. So it's not a linear relationship. When we talk about wave functions, the energy carried by that wave is proportional to the amplitude squared. So as waves get larger, the energy that it carries gets even larger more extremely. Let's go back to our little picture now, but now instead of talking about displacement and acceleration velocity, let's think about energy, okay? Here we are at maximum displacement. Notice that all the energy at this point is potential, kx squared, or in this case, ka squared. But please remember, when you look in the IB booklet, they're not going to use capital A for amplitude. They're going to use x sub 0, okay? Then I release it, and it's flying back to the middle. And notice now here, all the energy is kinetic energy. All this potential energy became kinetic energy. It has no more potential energy. It's just all kinetic. Life's good.
Still in that point, kinetic and potential.
At-
It's not all the way there.
But at equilibrium, that is the position where the spring would naturally rest. And so there isn't a push or a pull stored in that spring at that point.
Wait, that's equilibrium.
This is equilibrium right here. Yes, where x equals 0
But it's still flying this way.
because of its inertia. Okay? Great. And then it goes and compresses the spring, which then stores all that energy into the spring again, and we're back to maximum kinetic or potential energy. By the way, this is called elastic potential energy when we're talking about a stretchy object, okay? Before we were talking, what was the kind of potential energy we talked about before? Gravitational, which is in a gravitational field. Are there other kinds of potential energy you can think of? There's one that you studied with Andre probably, but we probably didn't call it this. Or Brent. There's chemical potential energy. Chemical bonds store potential energy as well, okay? And that's the energy we get when we eat, right? We're taking the potential energy of those bonds and turning them into the energy that we use. Good question. Okay. And then we're back. Oh, and notice here we are not at either. We're not in equilibrium and we're not at amplitude. We're in between. And the total energy is equal to the sum of those two. No, recognize that this is equal to this, which is equal to this. Yeah? Because you can't, remember, conservation of energy. It's not created or destroyed. It just changes forms. And since there's no friction, we're not losing any energy in the form of heat. And now if I was to make a graph, since we love graphs in physics, of energy versus time, let's look at it for a second. We're going to start up here at maximum displacement, and I'm going to graph my potential energy versus time, and it's going to do this. Yeah? Okay? I mean, it's not perfect, but that's potential energy, starting here. Okay? Kinetic energy is going to do this. Right? When I have no kinetic, I have all potential and vice versa. And if I was to look at the total energy, it would do something like this. No, because remember, the total potential energy you have is the total energy, or the total kinetic energy. And technically, it should always add up to that same amount, because energy is not created or destroyed. Yeah? All right. That's our introduction to simple harmonic motion and oscillatory motion and things vibrating. Now, this happens in all sorts of things in our lives. And so this is kind of what you need to start thinking about. And we're going to move this into wave motion and what waves do for us here in just a little bit. But one more thing I want you to think about is notice that all these graphs we've done, okay, and as you're doing the reading and thinking about the homework, you'll see this in there. All these graphs we've done, we've started with when t was at 0, we were at maximum displacement. But I could just have easily started my stopwatch when the object was here, right? How would that change my graphs? They would just shift, and that's called a phase change. And you'll see in the equations and stuff involved with this, they say, we'll talk about this next class, but I just want you to start thinking about how these things will shift from being a cosine curve to being a sine curve just by when I started my stopwatch. Okay, that's the only difference. And so you'll see that in the general equations for simple harmonic motion.